we're on the bottom of page 13 now. I would really suggest trying this page on your own first, this section, and then coming back and checking. Okay, I'm going to go through them kind of quickly because this is the practice section, not really the teaching section, but try it on your own and then come back. Okay, so looking at my first one, I see that we have arithmetic because we have an adding pattern with a d value of 2. So that means my explicit formula, a sub 1 equals d, which is 2, times n minus 1, plus a sub 1, and a sub 1 is 1. Recursion, I'm starting with a 1 to get to the next term. I take the term that came before it, and I add 2. So looking at my next one, we have a multiplying pattern. We are multiplying by 5. So, explicit formula, a sub n equals what I start with, which is 2, times what I multiply by, the ratio, which is 5. And we're starting with a sub 1, not the y-intercept, so we do an n minus 1 to balance it out. For recursion, we are starting with a 2. To get to the next term, I take the term that came before it, and I multiply by 5. So those were pretty quick. Said we've done a bunch of those. For 3 and 4, we're starting with the formulas. So remember, our place that we always go to first, we don't try to go back and forth between these two because we don't have a lot of practice with that. Go over and find your terms first. So I'm going to go back and make my list of terms. I'm starting with a negative 2. Now, this is, hopefully we can read this now. To get to the next term, I take the term that came before it and I add 3. So I'm adding 3 would be 1. Adding 3 would be 4. Adding 3 would give me 7. Okay, looking at this pattern, we can see, and we should be able to see from our recursive definition as well, that this is arithmetic with a common difference of 3. So to write my explicit formula, a sub n equals, we have the common difference times n minus 1 plus a sub 1, which ends up being minus 2. So looking at my next one, I have a explicit definition to start with. So I'm actually going to plug in those numbers, plug in a 1, plug in a 2, plug in a 3, and plug in a 4 to get the values. So 1 times 10 to the n minus 1. So n minus 1 is 1 minus 1 is 0. This is 1 times 10. 2 minus 1 is 1. 1 times 10. So I'm just doing, when I say the 2 minus 1 or 3 minus 1 in this case, I'm just doing that part. So 10 to the 0 is 1. 1 times 1 is 1. 1 times 10 is 10. 1 times 100. And then 1,000. So I can see here that this is a geometric pattern. I'm multiplying by 10 each time. Multiplying by 10. So when I write my recursive definition, I say I start with a 1 to get to the next term. And actually, I'm going to continue to write this, but then I'm going to change it to function notation just to kind of hammer home that you can write it either way. Okay, I multiply by 10. So if I was writing this in function notation, f of 1 equals 1. To get to the next term, I take the previous term and I multiply by 10. Okay, so that's just function notation, and I chose to do that in this one because the explicit formula was also written in function notation. So to finish this up, these are some trickier patterns. They're not just going to be a sub n equals a sub n minus 1 and then something else when you do the recursion. It's going to be a more complicated process. So if you want a challenge, you want to try these, I would pause the video, see what you can get done, okay? And then you can go back. And I even think if you can't get them on your own, just like seeing and thinking differently and watching me do it would be useful for you. So looking at A, should have tried this on your own already. The first thing I notice is that I have this pattern of adding 9 and then adding 18. And then here I add 36. Now that's really hard to represent. But what you can notice here is that when I do this, I'm multiplying by 2 and then adding 1. So this is true, the 9, 18, 36, and looks like it might be a lead, but the easier lead is that to get 8 times 2 is 16, plus 1 is 17. 17 times 2 is 34, plus 1 is 35. 35 times 2 is 70. 70 plus 1 is 71. And I can write that with recursion. So I still write what I start with, and then I write to get to the next term, I'm going to do 2 times the last term, and then I'm going to add 1. Okay, so that's neither arithmetic nor geometric. It's not as simple as that, but you can write it kind of similar to the other ones. So for the next one, we basically, what could happen from the one term to the next one? This one, if I divide by 2 and subtract 1, that works. So 22 divided by 2 is 11. 11 minus 1 is 10. 10 divided by 2 is 5. 5 minus 1 is 4. 4 divided by 2 is 2. 2 minus 1 is 1. So here, I'm starting with a 22. To get to the next term, I do half of the last term, and then I subtract 1. So the next one, I'm going to try to relate back to something we had in the last lesson. This one shows a pattern where I add 2, and then I add 3, and then I add 4, and then I add 5. So for this one, and once again, there are other ways to write these. As long as you write a recursive definition and it works, it's totally fine. Okay, these are just the ones I kind of came up with from the problems. So here, a sub 1 is 7. To get a sub 2, that's 7 plus 2 is 9. So I'm kind of doing some baby steps here. To get to a sub 3, I'm taking 9 plus 3 is 12. So what I notice here is that this number matches up with these numbers. So we can put an n here, and that will work. Okay, so the formula here, a sub 1 is 7. To get to the next term, I take the term that came before it, and I add the value of n. Okay, so that will work for that one. And our last one, this is actually kind of Fibonacci in disguise, because I add the 2 plus 4 together to get the 6. I add the 4 plus 6 together to get the 10, and the 6 plus 10 together to get the 16. So it just starts with different things. So instead of starting with a 1 and a 1 like your traditional Fibonacci, we're starting with a 2 and a 4. And then to get to the next term, I take the previous term and the one that came before it. Okay, so this is basically exactly Fibonacci, except we have different starting values. And to define this one, you do need to define 2 terms, not just the 1 term, which is another type of recursive, just a little bit trickier.